Hi everyone, today we are going to look at how we can design the relational database for MySQL. Uh, Relational databases can be designed and implemented on MySQL in a typical the steps and procedures. Let's start with the conceptual design. Conceptual design, we use ER model, entity relationship models. And database model, we need to select. Our selection is a relational database model. Once we select the relational database, then we need to convert conceptual model to logical model. Conceptual model is the ER diagram. So conceptual model is ER diagram, entity relationship diagram, so-called the ERD. And then relational design can produce relations schemas. In relational database, relation means table. So relation schema is nothing but table schema. Schema is nothing but the structure or description about table. From ER diagram consists of an entity set, which is rectangular, and then relationship, that is a diagram, something like this. From ER diagram to relation schema, that is called logical design. Then we need to select the DBMS, database management systems packages, software packages. The database management system software packages that we want to use is MySQL. So based upon MySQL, now we need to create database. There is a language that we can create database, which is called data definition languages. So we need to create database, create tables, and populate the data. So sort of we have a database now constructed. Then we can pose an SQL, structured query language, to this database. Then this database return to us a result, query result. Structured query language, the SQL, is a kind of data manipulation language. Data manipulation languages. Data definition language is to define database and tables, and also physical design here. Once data populated in the database, then we can manipulate it. What we need to do, physical design, therefore we can improve the performance. Improving the performance is nothing but to speed up the database return time. In order to access data fast, then data needs to be stored in a database effectively. So for example, we want to make our database in well-structured. There are many different structural algorithms have been designed and implemented, and not the data can be stored sequentially, or not the stored in a way the data is inserted, but we need to restructure, reshuffle the data so that data can be accessed quickly. We can make our database in certain tree structures, B tree or B plus tree, like a balanced tree. B tree is not like binary trees. B stands for balanced tree. So structures of a tree can be balanced. But anyway, that is a physical design. Physical design definitely needed if we have massive data stored in our database. And also if we want to improve the performance. Unless otherwise, for the small toy databases, we don't need to. In other words, the sample data that we are working on, this class, we don't need, right? So we start with the EL entity relationship model, widely accepted, and first invented by Peter Chan when he was in Harvard University students. There's a graphical representation. So it has entities and relationships. EL model can produce a graphical output, which is called the EL diagram. This EL diagram has the rectangle for entities, diamond for relationships. So we have here entity instance is a row in a table. Entity set is a collection of entities. And connectivity levels type of relationships. Diamond that connects the entities. So we can consider a real-world database, for example, the college or university database. It has a department, a class, and the students can take a class, and department offers some courses, and students is associated with the 8 departments. So it could be like these EL diagrams. So department, faculty are affiliated with a department. Department where there are students are majored in. So department offers major to student. Students take their study major from a department. So the way that I now interpret, actually that interpretation is the scenario in this data flow. So analyzing the scenarios, data flows, then we can construct this kind of relational database. So from storytelling, we can generate EL diagram. If we look at the EL diagram, then we know how to interpret it so that we can tell the stories based upon EL diagram. That's what I am now trying to do. Looking at this EL diagram, I can generate stories. Faculty is affiliated with the department. Department hires faculty members. Faculty teaches a class, which is offered, which is taken by the students. Students also belong to a department. We can make stories clockwise, counterclockwise. We can start from anywhere. So all of those things can be a story. Given that EL diagram, then it is more specifically, we have a relationship and entity sets. Each of those, the objects can have the attributes. So student can be defined over CWID, department, and major. Instructor ID, faculty ID, name, and department. And enroll, we have year and semester. So students can be enrolled a class which is instructed by the faculty. Faculty can take a group of students, so students enrolled. So each of that enrollment can be for a specific semester of year. So outcome of logical design is a schema. So we have the relation schemas for student, department, faculty, class, enroll. Then we have each. This is a schema. Schema consists of the attributes. Attribute schema is a set of attributes paired with the attribute type. Okay. So CWID, we can say integer, name, text, major, text, for example. And department can be defined over department name, department ID, department chair. Faculty is defined over faculty ID, name, and affiliation. Class, class ID, class title, or we can say CRN, or instructor. Enroll. Student can be a CWID. That is a primary key. Underlined, that is a primary key. This primary key CWID may appear in another table, enroll. Then this attribute CWID in the enrollment is called the foreign key. So we have a primary key and foreign key. Attribute which is first and originally defined in is a primary key. So CWID maybe is the primary key in the original table students, but it can appear also in another table. Then the value of this CWID is dependent on the value of the student ID. What it means is that, let's say if anyone wants to enroll a particular class ID. So student ID, if you want to enroll with a certain integer, then this integer, which is CWID, maybe CWID, that integer should first defined in the student table. That is quite true, right? In order to enroll a particular class, then the students needs to be in the student table first. Then that students can enroll a table. Same thing, faculty member, faculty ID, name, and affiliation. Then faculty ID is a primary key here because that is underlined. Faculty ID can identify the faculties, right? Faculty has affiliation. So faculty is affiliated with a specific department. So affiliation is nothing but department ID. If you want to define a faculty ID and name, and affiliation, whatever, cyber security. But if there is no department called cyber security, then this is impossible, right? This affiliation is a foreign key. Value of the foreign key here should first defined in its original table. So in the original table, the department ID should be first defined, say cyber security. After that department is created, then faculty member can be affiliated with that department. That is also quite true, right? That makes a lot of sense. That is a primary key and foreign key that can be defined in a relational database, and specifically in reality, if we use MySQL, then we can define it in MySQL. Similarly, if we define students, then student has major. This student major cannot be any value that these students can choose. Student major should be first defined in the department. So cybersecurity is a major. Then department of cybersecurity needs to be defined first. After that, So say we define department. After that, we could define students because this department ID is in the student table a major, which is a foreign key. Same thing here. Once you define department, then we can define faculty. This is number two. Student and faculty, there's no order. But between student and department, there should be the order. Department first should be defined first, because the other depends on this primary. Okay. And then class can be defined. Class can be defined here. At least we need to say this should be number 3. Why? Because class as instructor. Instructor should be from the faculty ID. Okay. So after faculty is defined, then we can define, hey, here's a class and instructor can take that class. Enroll, that will be the last one here, 4, right? Because CWID is a foreign key, so at least this enroll should be defined after the students. But enroll has a CID. CID is a foreign key again here. Its primary key appears here in class. So this is primary key. So class should be defined before enroll. So this is the 4th one. For simplicity, I think we don't need to consider this. If we consider this, for example, FID is a primary key. Chair is foreign key, for example. Then we have a foreign key here, and department is a primary key. If it is the case, then department says, oh, in order to define department, there is a chair, which is a foreign key that depends on the primary key, which is a faculty. So in order to define faculty, then faculty says, hey, we have an affiliation, which is a foreign key. Its primary key is a department. Department says we need the faculty should be defined first. Faculty said, hey, we need to have a department to be defined first. It's cyclic, so it's not possible, right? So we can say, hey, in our practice, forget about this. So there is no the connections, no relationship between chair and faculty IDs. But anyway, this kind of design, we call this is relation schemas. Okay. So we have a schema. While relational database have been widely used, so popular, so it is well reputed, and it runs robust. But it is a little bit of the issue in relational database. Relational database has a weakness in its representation. It is because basically relational database consists of tables, relations. Relations is nothing but tables, right? If it is a table, then table is nothing but columns and rows. Each column has an atomic value. Column cannot have more than atomic values. Okay? But some other cases, we want to, in the real world application, column may be a multi-valued, or column may be composite values. What that means is that in the column of student has, for example, phone number, phone. Then phone, we can think of, oh, student has only one phone. Then that is a atomic values. But some other students might have more than one phone. Think about the column name phone. Then one value can fit in. What if student has multiple phones? Personal phone, company phone, or some other phones, 2 or 3 different phones. Then that attribute should allow a set of phones. But relational database, for each column, the value should be atomic. The value itself. There's no way that we can have a set of values. Also, there's a composite values also possible that is in the real world application, but that is not possible in relational database models. Example is this: address. Address in a table, if it is a column, then that should be one value. 555 Broadway, Dobbsbury, New York 10522. All things should be one atomic values. If we are okay to use, there is a long length of address as an atomic value, that's fine with us. But some cases, we may use part of the address values. Some cases, we may want to decompose that address values, each small chunk, like street, city, zip code, state, country, whatever, right? We may need each individual small, or sometimes we want keep that long list as a one atomic values. So those things cannot be flexibly allowed in the relational database. Either we need to choose, for example, if there is a multiple phone, then we can say phone 1, phone 2, phone 3, phone 4, phone 5. Maximally, there may be 5 phones available. Then what happens if most of our students has only one phone? Then there are a lot of empty values. Phone 2, empty. Phone 3, no values. Phone 4, no values. At the same time, the address. If the address as a whole, one attribute, fine. But because some other times we need to use each small chunk of attribute, the address values, then we need to choose one or the other. That is some of the drawbacks. That is the weakness of a relational database. To overcome that relational database, then we need to think of object-oriented database. Object-oriented database. One of the composite attribute here, relational database, if we say major, then we think of only atomic value, major, cybersecurity. Cybersecurity is taking one value and we can say, oh, that is the major of that students. But in the real world, which department are you associated with? If we ask students, then this is my major. What is your major? Major is simply atomic value or department itself. We can say department itself. So type of major is department, which is a relations. Okay. Faculty. Faculty has affiliated with the department. So department is a type of this department as well. Okay. If we see enroll, then CWID, rather than the ID itself, we can say type of that is a student. Student is a CWID. CID is nothing but class. So we can say here, rather than CWID, we can say student. Students enrolled in a class. Okay, so So object-oriented database type, not necessarily an atomic like integer text, but it can be a composite, can be another class. That is an object-oriented database design. So OID is object identifier. Here using object and IDs. Okay, so this is what I'm saying. Student says the department. Department is nothing but this entire department. So this entire department can be this. Department is entire. If we say faculty, faculty is entire of this. So object-oriented databases design can accommodate any length of any level, any degree of complexity of the real world. So complicated real world structures can be represented in object-oriented database models. That is a strength of object-oriented database. Okay, so comparison between relational database, object-oriented database is, if we think of the representation itself, then, for example, major type text here, but major type in object orientation, there is a department, which is the department here, this and this. Here, relational database, all the type should be from primitive. So only primitive type can be used as a type for attributes. Object orientation, type for an attribute could be primitive type or could be type that is defined by itself. So type department, but this department type is defined by defined itself here. So we need to first define department, and then we can define student. Therefore, this department can be understood by previous definitions. So representation-wise, object-oriented database is the winner, which is the strength for object orientation database. What about usages? How can we use? The way that we can use relational database, we use SQL. SQL is very, very simple. This is a strength of relational database. What is an SQL expression? SQL expresses only what we want. SQL does not require how we get the result. There's no how is not needed for SQL expression. SQL needs only what we want. What is needed? How is not? That is SQL statements, which is simple because I want this. But in object-oriented database, then by having this, we need to go to this department. When there is a faculty, then we need to go to faculty again. And when there is a department, we need to come back to department again. Lots of the connections from one to another. Therefore, we need to chase all those things. It's not the simple that we say, hey, I want this. But in object-oriented databases, we need to specify which way that you need to walk through. Therefore, we can get the result. So complicated. Query in object orientation. So there are some queries available. For example, OQL, object query language, rather than SQL. Language-wise, user access-wise, relational database is the winner. So between relational database and object-oriented database, there is a trade-offs. The way that we can use, then a lot simpler here, relational database. The way we represent, a lot simpler here in object-oriented database. Trade-offs. Okay. So relational database, for example, faculty ID, name, affiliated, title, year, author. Um, this is a course. This is a faculty, like this. But in object orientations, we have the faculty 1212, John, name is John, affiliation, cyber, the book, this is a book. Book, this guy, we have two tables, right? Faculty tables and publication tables, for example. In relational database, if we want to see what kind of publications written by John, then we need to pick name John here and then match John with the author here. So we have two matches, and then we can say Java and Python. But this is relational database. Relational database versus NoSQL. NoSQL is like this. Simply, in other words, it could be a JSON type. This kind of representation tells about these two tables. So faculty ID, name, John, affiliated, and book. The value for book is a list. See here, if we think of this in Python, JSON in Python, then book is a multiple publication. So we have list here and there, list. List has two items. Those two items are in a dictionary formats. So title, Java, year 2015, that is the first element. Second element is title is Python, publication year is 2020, second element. So each element can be represented in a dictionary. So key and value pair. Entire here is a key and value pair also. FID, attribute name, this is a value, this is attribute name, this is a value. That can be represented here. This is attribute name, value is 1212. Attribute name is name, value is John. Attribute name is affiliated, value is cyber. So affiliated, colon, cyber. Key and value pair. Think about Python, then key and value pair. This is a pair. That is this. And book, entire. So this is connected with that through this common attribute in relational database. But it could be, say, book, publication for these faculties. The value for book is not just atomic value, but entire data itself, entire table. So book is a list of a publication. So each publication will be the value, key and value pair. Title, key, value Java. Title, year, value 2015. Title, author, value John. Here in this case, author, we don't need to, because we, instead of sharing common values in relational database, in NoSQL, we stick the value together with this. Rather than splitting into two relations, we plug in to this John. So to John, we plug this book information, publication information, with two elements in the list. That is NoSQL. That is what JSON format is. This can be rewritten in this way. This is a little, we call it pretty printing. FID 1212, name John, affiliated cyber, book. Then we have, this is the first item, this is the second item. The book has two elements. First element is a dictionary, so title, Java, year 2015. If you have more than one, fine. You can plug more and more here for the publication. So in this way, we consider database models, and we see the difference: relational database and object-oriented database, and also NoSQLs, how they are illustrated with specific examples, so that we see the representation-wise which one is good, and access, which one is good. NoSQL here, the real access this is not by the language of, for example, SQL. SQL is not working for this, right? This needs somehow like codings. By codings, we can access, we can get the values from the keys in this kind of JSON files. So even more complicated for database access. So relational database, the language-wise, very, very simple. Data representation-wise, object-oriented database is powerful. I would not say it is simple. Of course, it cannot be simple, right? But it is powerful. We can do almost all real-world application types. JSON types. This is simple somehow, but it is very strong in data sharing among many other independent servers. Rather than sending out, for example, Excel files, we simply send that plain text JSON files. Then the opponent server can understand. So this kind of JSON is the type that we can use to share data among many different services. Okay. I think this is it for this week's lecture. Okay. I will see you next time.